Hi folks, we're going to take a look at number 20 from page 221. Okay, so let's read the question. It says the surface area of a cube is changing at a rate of 8 centimeters per second. Okay, so right off the bat, I know I'm working with a cube. So draw myself a diagram. Okay, and since I'll probably have to be working with the dimensions, make sure you add them on to your diagram. And since it's telling us that the surface area is changing at a rate of 8 centimeters squared per second, that means that what I'm given is the derivative of the area with respect to time. Okay, and that's 8 centimeters squared per second. Okay, it says how fast is the volume changing when the surface area is 60 centimeters squared. Okay, now often when we're doing these problems, we have a direct relationship between the two values that we're considering. In this case here, we're trying to relate the volume and the surface area. Now, we don't have a direct relationship between those two, but we know that both the volume and the area depend on the side length. Okay, so that's how I'm going to proceed. So I want to determine the rate of change of the volume. So I know that that's given by x cubed. Okay, but all the information I'm given is with respect to the surface area. Okay, so what I'm going to try to do is use a relationship between area and the side length to rewrite this equation. Okay, so we know that the relationship between area and side length of a cube, well, all sides are the same and there's 6 sides, so it's just 6x squared. So that means that x, if I solve for this, would just be a over 6, and then I take the square root of both sides. Now here, since we're talking about a side length, I don't bother with the negative square root. So that's the only reason why I'm only considering the positive square root. Okay, so now what I can do is I can now rewrite my equation for volume in terms of the surface area. Okay, so we have x, which can be written as the surface area over 6, and all of this is being cubed. Okay, now in order to take the derivative more easily, what I'm going to do is I'm going to rewrite this as a over 6 to the exponent of 3 over 2, because square root, of course, can be represented by the exponent 1/2. Okay, so now I've got my relationship between volume and area directly. I'm now going to take the derivative of both sides in order to determine the rate which I'm looking for. Okay, so I'm given dA dt, and I'm looking for dV dt. So let me take the derivative with respect to t of both sides. Okay, so this straightforward. On this side here, though, I have to be careful. I'm going to have to use the chain rule. Okay, so first I'm going to have to take the derivative of a over 6 to the 3/2 with respect to a, and then I'll take the derivative of a with respect to t. So let's take this derivative here. So it's 3 over 2 times a over 6 to the 3 over 2 minus 1, 1/2. And then, of course, using the chain rule, times the derivative of a over 6, which is just 1 over 6. And now I have to multiply that by the derivative of a with respect to t. Okay, so I actually applied the chain rule 2 times. Okay, so let's simplify this out and let's input what we know. So dV dt is what I'm looking for. Okay, so here we got the 3 and the 6 reduced to 1/2. Okay, so here I've got 1 over 4 times the square root of a over 6. Okay, and I know that the area is changing at a rate of 8 centimeters squared per second, so I can replace that by 8. Now, of course, I'm looking, so first of all, let's take a look. We have this relationship now between the derivative volume, derivative area, but it also includes this unknown a, okay? But they gave us this information in the question because they're not just asking us how fast is the volume changing, they're telling us specifically when the surface area is 60 centimeters squared. Okay, so they had to give us that information in order to solve this. So now I can just, well, first here, 8 over 4 gives me 2. So this is 2 times the square root, and they're telling me that it's 60 centimeters squared, the area at the given moment, over 6. So this gives me 2 root 10. Okay, and since it's volume with respect to time, using the units that were given, it's going to be centimeters cubed per second. Okay, now because this is a straightforward math problem, okay, there's no context to this cube, the expectation is that you're giving me an exact solution. Okay, so we'll just pan out here so that you can see the full solution, and we'll just recap what we did. Okay, here we had to take a bit of a circuitous route because we first had to start with our relationship between volume and side length, and then from there we use the relationship between area and side length to rewrite V in terms of A. And then from there we could proceed with the calculus. Okay, so that's it for this one here.